So, yesterday we started in on the packet that I gave you. We said that that packet talks about the examples and some of the applications of Newton's laws, and that's what section 5, or the second section in chapter 5 is about. So the first thing we talked about was weight, and we said that weight is by definition the force that is exerted by gravity. Gravity causes a force, and if that force is not balanced, it will cause an object to accelerate, speed up, slow down, change direction, any of those things we talked about. We talked about the idea that you can calculate the weight of an object, or how hard gravity is pulling on it, by taking the mass of that object and then multiplying it by the acceleration of gravity. Here on Earth, that number is 9.81. Okay? That number will give you the force that gravity is pulling on, and that's why weight is measured in newtons, because it is a force. Right? Next part we talked about was the difference between weight and mass, that a lot of times they get used interchangeably, but they are different. Weight being a force, that force by gravity, but then mass being a measurement of the inertia of an object, or how hard it is to get it to do what it's doing, or change what it's doing. And we talked about the idea that the mass of an object will not change based on the location. That an astronaut, in this case here, right, has the same mass, but because the effect of gravity is different in those two locations, the weight will be different. Good there? And we did a couple of examples where we calculated the weight, or the force of gravity acting on something, by taking that object's mass and multiplying it by 9.81, right? But then, when we go to analyze the motion, right, using Newton's second law, that force, that weight, the force of gravity, just gets factored into Newton's second law just like anything else. Right? That it's no different, it has a direction, it has a magnitude, we treat it just like anything else. Okay? Good there? Towards the end of the period, we didn't even get to this far, did we? Okay, all right. One of the forces that we deal with a lot in conjunction with gravity is normal force. So for example, this book that's sitting here on the desk, or this can of soup that's sitting here on the counter in this picture. Currently, that object is not accelerating, right? Its acceleration is 0. It's not speeding up, it's not slowing down, it's not changing directions. Okay? That being the case, what else needs to be 0? If the acceleration is 0, the net force has to be 0 as well. There is a gravitational force that is acting on this can of soup. And we learned yesterday that we could calculate that gravitational force by taking the mass of that object and multiplying it by the acceleration of gravity. We don't know what the mass of that can of soup is, but that's how we would calculate it. Now, with that being the case, if that can of soup is sitting there on the counter, or if this book is sitting here on the counter, right, and it's not accelerating, can this gravitational force be the only force acting on it? Because the net force wouldn't be 0 then, right? There has to be another force. How big does that force have to be? Equal to gravity, but which way does it have to act? In the upward direction, right? So if we're talking here, we would have another force that would be just as tall as gravity, but pointing in the other direction. In the case of the book sitting here on the counter, or in the case of that soup sitting on the counter, where does that upwards force come from? The table, okay? And because it is a surface, like a table or a floor or a chair, we refer to this force as the normal force, F sub n. Okay? It's normal because in math class, if you talk about something being normal, that means it's perpendicular, right? Normal forces are always perpendicular to the surface that they are caused by. So in this case here, in the case of the book, there's a force that points straight up from the table, right? In the case of you sitting in your chair, the chair is pushing straight up from the surface of the chair. In the case of me standing here on the floor pushes straight up, okay, always perpendicular. Now, how big that force is depends on what else is going on. So here, a 9.3 kilogram child sits in a 3.7 kilogram chair. Her feet do not touch the ground. So let's draw a little picture here. And here's the floor, and here's the chair, and yes, it's floating, I know. And then here is the child sitting in the chair. Okay? Even though it doesn't specifically say, right, we can assume that this child is not moving up or down, right? That they're sitting there motionless. Meaning that the acceleration of that child is going to be equal to what? 0. Okay? So what we're going to do here, part A says, draw a free body diagram for the child and find the normal force exerted by the chair on the child. So I'm going to take my child down here, separate it from the rest of my picture, okay? And a free body diagram deals with forces, right? So what's the first force that we can draw that's affecting this child?
Gravity.
Let's draw gravity, right? Margo, which way does gravity act?
Downward.
Straight downward, right? So we'll draw a force, it looks just like this, right? And we said that sometimes you'll see that force labeled as W because it's the weight of the object, but we can also call it F of G, right? Because it is a force, it's just the force caused by gravity. How do we calculate the force caused by gravity acting on an object? It is MA, but it's a specific A in this case, right? It's that mg, right? Because it's the force or the acceleration of gravity. Do we know the mass of this child?
Yeah.
9.3, is that what it is?
Yep.
Okay, so we can plug 9.3 in for the mass, right? And then we know that the acceleration caused by gravity here on Earth is 9.81, right? Okay, that's the g value. Right now, it's not really anything. Right now, we're just finding out how big, right? Jamie, do you want to make it negative? Why?
Did you say the upward one's positive?
We can call it that, right? We said that the negative just tells us what? Direction, right? So in this case here, if you want to call it negative, you can, okay? Or just by virtue of the fact that, how have I drawn this arrow? So can you tell which direction it's going? Yeah, you can, right? If we kind of talked about yesterday that in the picture, we can tell which direction these forces go from the picture, right? From which way the arrow points. The positives and negatives really become important or more important when we start doing the calculations with them. Because now we can't tell just by looking at the number which way it goes. But Jimmy, if you want to make this negative to begin with in the picture, that's fine. If you just want to be consistent with it, that's perfectly fine. You can do that. Okay. Did we get a number here? Okay. So 91.2. Okay. Now, as the child sits in the chair, right? We discussed the idea. What is that child's acceleration? 0, right? So, can this be the only force acting on her? Can't be, right? There has to be another one. Which way does it have to point? Up. How big does it have to be? 91.2. Why? Because that would give us a net force equal to 0, right? Where does that force come from? The chair, right? The chair that she's sitting on. So that would be a normal force because it comes from a surface. And in this case here, it would have to be 91.2. Now, some of you, right, might be thinking, because I know this question comes up, right? When I ask the question of how big does it have to be, some of you, your first reaction might have been at least 91.2. Okay? But can it be anything different than 91.2? If it was bigger than 91.2, what would start happening? There would be an upwards acceleration, right? Because then we wouldn't have the forces balanced. So that normal force doesn't have to be at least as big as gravity. In this case, it has to be exactly as big as gravity, so that the net force equals 0. Good there? All right. Part B of this question says, draw a free body diagram for the chair. Find the normal force exerted by the floor on the chair. So I'm going to take my chair and bring it over here, and now I'm going to make a separate free body diagram for my chair. First force we can put on this diagram is what? Gravity, right? Gravity is going to act straight down. This is the force of gravity acting on the chair. Right? That's where the extra c is coming from. And we calculate that by taking m times g, but in this case the m we're talking about is going to be the mass of the chair. Did they give us the mass of the chair in the problem? They did, right? I think it's 3.7, is that right? So we take 3.7 times 9.81, you run that through and you get, what is it, 36.3? Okay. So that's 36.3 newtons. That's the force of gravity that is acting on the chair. But is that the only downwards force that's affecting the chair? Right? What else do we have to kind of contend with here?
So we have to add the Newton's force.
Right? This kid that's sitting on the chair is also pushing down on the chair, right? How big? 91.2. All right? Good there? So now, there has to be an upwards force, but how big does it have to be?
127.
127.5. And we got that by how? We have to end up with a net force equal to 0. In this case here, there are two downwards forces affecting that object. But there's only one upwards force. Where is that force coming from? What keeps the chair from falling downward? Nope. The floor itself, right? That means that we can call this force here a normal force. It comes from a surface, or a table, or a chair, or a floor. Okay? And in this case here, that force is going to have to be 127.5. Because if the chair doesn't move, what does the net force on the chair have to be? If the chair doesn't move, what does the net force on the chair have to be? 0. And therefore, we have to have just as much up as we do down. Good there? Okay with that so far? Okay. The next page, some word stuff here that talks to you about something called apparent weight. All right, so let's do a little demonstration here. This mass right here is 500 kilograms. Or sorry, not kilograms. It's a lot of kilograms. 500 grams, right? Half of a kilogram. This is another 500 grams. It's another half a kilogram. Okay? So there's 1 kilogram here plus the 50 grams for the hanger that I'm holding it on. Gravity acts on this object with a force of 10.3 newtons. Okay? Good with that? This is a scale similar to the scale that's at the grocery store, like in the produce section, or you can, if you want to find out how much apples you're buying, right? So if I hang this on here, okay, I get a reading a little bit over 10, right? It's not the greatest scale in the world, so it's a little bit bigger than that, but you got that. Okay. Question. Is this scale measuring the gravity that is acting on this mass? What was your first instinct?
No.
No, right? Is gravity still acting on this mass,
Yeah.
even though it's not hooked up to the scale? Yes. Is this scale reading anything? No, right? This scale is not reading the amount of gravity that is acting on this mass. This scale reads how hard it's pulling up on that mass. Okay? Now, as we sit here, motionless, is the force that this scale is pulling up any different than the force of gravity pulling down?
Is it equal?
It's equal, right? So I see, yeah, so, okay. It has to be equal, Joe, just what has to be different?
The law of direction.
Direction, right? Gravity pulls down, this scale pulls up. If they pull the same amount, that means the net force on this thing has to be what? Zero, and it doesn't accelerate, right? Voila. Okay? However, I'm going to change something real quick, because this is less than ideal, as you can tell. Nice. Wait, or no, go ahead.
Do people research like why there's gravity and stuff?
Say again.
Do they research like why there's gravity?
Ooh, why there's gravity. Ouch. That's a tough one. We don't know that. We know that there is gravity, and we know how much gravity there is,
Not what causes
but
it.
not what causes it. We really don't have any reason why these two masses, the mass of the Earth and the mass of these things, should pull each other together. We really don't know. Okay? That gets into things like string theory, and have you ever heard of like string theory and stuff like that?
Kind of.
So that's
Oh,
that,
string theory.
get, so that gets into stuff like that. So, all right. So right now these two forces are balanced. If I want to make this mass go up, right? How do I make this weight go up? How do I make these masses go up? Pull up, right? Well, if I want to make them actually physically move upward, right? Sorry. How do I make these two masses move upward? Pulling, right? I have to apply a greater force. So, as I move these things upward, right, we should see a jump in the scale. Ready? Here we go. All right? The very first thing that happens is that the red needle goes where? Goes higher, okay? But, what are these masses doing now? But it's moving, right? What was the difference? Okay. The second time, when those masses are moving upward, they are moving upward with a constant velocity. Constant velocity means the acceleration is what? Zero, so the force is balanced. Once we start them in motion, they continue in motion. Okay? Next. All right, here they are. Now I want to move them downward. Okay? What do I have to do? There has to be a net force acting downward, right? Can I make gravity bigger? Can't change gravity, that stays the same, right? But if I don't pull up as hard, if gravity stays the same but I decrease the upwards force, now there is a net force in the downward direction, right? So if I start moving these things downward, what should we see with the red needle? Ready? Here we go. Did it move that way?
Yeah.
Right? Okay. Like I said, this scale doesn't measure what gravity is pulling on that object. It measures what it is doing to the object. And based on the movement, we can change what that scale reads. Just like your scale at home in your bathroom, or wherever you have it, if you have a scale at home. Okay? When you're standing there in your bathroom in the morning or at night or whenever it is, okay, are you moving up or down? When you're not moving up or down, the net force on you has to be equal to 0. There's a gravitational force pulling down, there's the scale pushing up. In that case, those two forces would be the same. So when the scale isn't moving, or when you're not moving, those two forces should balance, and it will tell you what gravity is pulling on you. But if we take it to a situation where it is moving, like an elevator, or a roller coaster, or the power tower, right? That scale wouldn't read what gravity's pulling on you, it reads what it's doing to you. Okay? Everybody ever been on an elevator before? Yeah? Okay. If you've never been on an elevator, just zone out for a second or something, all right? Just, yeah. But especially this sensation is more pronounced in a fast elevator. Like if you've ever gone to the Empire State Building or Sears Tower or the St. Louis Arch or something like that, okay? That's a really tall elevator, right? I suppose we have a couple tall buildings here in Cleveland, but you know, whatever. So, at the very beginning, when that elevator first starts moving, you get a sensation kind of like you're being pushed into the floor. Does that sound like familiar? Right? Or if you go on the power tower at Cedar Point, if you take the up power tower, right? It feels like you're getting like pushed down into your seat, right? Or if you go on the witch's wheel, right? I hate the witch's wheel too, but I'm using it as an example, right? When you go down on the bottom part of the witch's wheel, it kind of feels like you're getting like shoved into your seat. You know what I'm saying? Because it's not so much that something's pushing down on you, it's more that your seat is pushing up on you, because it has to overcome that gravity. But when you go over the top of a roller coaster, or like, you know, like those little bumps at the end of the Blue Streak, when you're coming into like the station, you know what I'm talking about? Anybody ever ridden the Blue Streak before? Come on. Yeah. So, I mean, well, just don't wear the seatbelt. It's a lot better, okay? Not that you should do that. It's unsafe, all right? But that's why I'm saying it's unsafe not to wear your seatbelt on the Blue Streak. Okay? But if you didn't, right, if you were a thrill seeker and a rule breaker, first you would take off your ID, right? Then you would go ride the Blue Streak, all right? So, right? But that sensation you have on any roller coaster towards the end, like when you go over those little bumps at the end, where you're kind of like floating for a little section, where it almost feels like you're kind of coming out of your seat. Yeah, I don't really like the Mantis. Yeah, I don't like that. So, yeah. So. You feel on the Mantis? Just in general? Yeah, like the Magnum at the end. You know, I mean, let's face it. When you take into account like how good the ride is and how long of the wait it is, the Magnum's a pretty good ride. I mean, because you never wait more than 10, 15 minutes, and it's so good. Like Maverick's just too long of a wait. I mean, like Millennium Force. Like, I mean, it's. See, I don't. The one thing I don't like about Millennium Force is that, like, after I'm done and I get off of it, my face feels like this. There's like little like tears coming out. So.
Yeah, there's bugs.
Yeah. One year actually, when we went with physics, we were riding the Millennium Force, and I was riding with Schober, and we're like coming in right at the end, you know, like when it comes around that loop, like right towards the end, you know, and we're like coming around, and all of a sudden, like a bunch of crap like hits us in the face, and we're like, it felt like a spider web, and we're like, that can't be a spider. Like, spiders couldn't have, like, spun a web since the last time the roller coaster came through here. What happened was, when we were going around the corner, apparently one of the wheels, like, it has a tendency to do this apparently, because they told us it happens a lot. One of the wheels, like, melted, and, like, little, like, plasticky stuff, like, flew back. There was like plastic, like, stuff all in our hair and stuff. We're like, what is going on? Yeah, it was, all over my hair. That's why I had to do this. I couldn't get it out. I was just like, zero. So, it was the worst experience of my life. I was in Schober's hair, okay? All right. It was just on my face, so. But anyway. Yeah, it was, So. But anyway, that sensation of that floating, like, feeling, right? Or that sensation of you getting, like, pushed down into your seat is what we refer to as apparent weight. It's not that the force of gravity changes. Apparent weight is, where are we here, okay? This sensation of having a different weight due to the force exerted on you by the floor is referred to as apparent weight. It's a change, not in the gravity that's acting on you, but on the other forces, specifically the normal force. And that causes this change in sensation. Okay? Good there? All right. Next thing. Right there. Okay. Next topic that we come across is equilibrium. Equilibrium is a real easy topic. Right? Key point. What is the condition for an object to be in equilibrium? Key point. An object in equilibrium is subject to zero net force, or the net force acting on the object is equal to zero. Flip that page, next page. There you go, right up at the top. So, an object is in equilibrium if net force is equal to zero. That's the condition for equilibrium. Now, when we talk about equilibrium, it can be a little bit confusing. If net force is zero, what does that mean also has to be zero? Acceleration. So there can't be any change. Is this book in equilibrium?
Yes.
Yes. Object is at rest. That's a form of equilibrium, right? But what else would fit the definition of equilibrium? Not accelerating, or if it's moving, but moving how? Right? An object moving with constant velocity is also in equilibrium. So equilibrium can either look like an object at rest, or it can look like an object moving with a constant velocity. Both of those are equilibrium. If we drew the free body diagram and looked at the forces, an object at rest and an object moving with constant velocity would look the same. All right, good there? Okay. All right. There aren't as many problems in your book that I like for equilibrium, so I got a couple of my own. There's one right underneath this section of equilibrium that talks about this engine that is being suspended in a garage. So it says a car engine is suspended in an auto shop by two chains. Never has this been a problem until this year. All right? Just so I know, this problem, never has this been a problem until this year. So,
You know what 2 chains is?
yes, yeah, I'm good. So, yeah, I'm good. So, I couldn't like do a rendition or anything like that, but not that I would if I could. But
You can do it.
no, I can't really. Honestly, I don't have the ability to. I mean, I know who 2 Chainz is, but couldn't, like.
Actually, anyone has the melody, so.
Well, so that's right. Yeah, so. All right. So it says the chain labeled T2 is completely horizontal. The other chain makes an angle of 60 degrees with the ceiling. If the mass of the engine is 224 kilograms, what is the tension in each chain? So this problem is asking us for 2 things, right? It's asking us for tension, but it's asking us for tension in each chain, okay? Tension is just a fancy word for force. All right? It's force that comes from a string or a chain or a rope or something like that. Okay? So, two unknowns in this problem. We want the force of T1, but then also the force of T2. Okay? Things we know. Mass of the engine, 224 kilograms. And then it gives us a little bit of information about chain labeled T1, 60 degrees with the ceiling. So I'm going to call that theta 1, right? I'm going to use that theta symbol to represent angles. So theta 1 is equal to 60 degrees. Okay? What we're looking for, what we know. Now let's give ourselves a free body diagram to analyze the forces. This ring that's connecting all these chains together, I'm going to call that the middle point, and I'm going to draw my forces from there. So, first force we can put on here. Like that, right? Okay? Let's add that gravitational force. I'm going to make it a little bit smaller. We learned earlier, right, that's a force of gravity acting on that engine as it hangs there. And we learned how to calculate that force, right? How do we calculate that force of gravity? mg. The mass of that object times the acceleration of gravity. It told us that the object was 224 kilograms. We know that g is 9.81. So therefore that force of gravity, we can calculate what that is. Borgo, you got it for us?
2,197.
Like 0.4, right? Okay. We'll go with all that, even though it's too many sig digs, but we'll go with it. Okay. All right. So we got that force acting straight downward. But then there are two other forces. Each of these chains, right? Tension is a pulling force. So it tells us that T2 is completely horizontal, right? So when we go to fill in this force, we would draw it in like that, because that's what T2 is doing. We don't know what T2 is yet, right? But we know it pulls that way. And then we have this one, right, that's pulling at an angle like this. We'll label this as T1. Okay? So real quick, before the bell rings here, okay? First, is this engine moving? Is it accelerating as it hangs here? Meaning that we would say that this object is in equilibrium. And we just learned that equilibrium means net force has to be equal to 0, right? Because there's no acceleration. So then f of g plus f of T1 plus f of T2 all together have to equal 0, right? But we run into a little bit of problem here. Yes? What's our problem? So you got two unknowns, right? But also, when we look at this picture, is adding gravity in T1 and T2 going to be an easy thing to do? What are we seeing about how all these forces are pointing? All kinds of crazy directions, right? There's a way we can do it. We'll talk about that tomorrow. Okay? Cliffhanger.